Hello and welcome, everyone. My name is John Butler, and I'm the Communications Manager for Clean Energy here at Swagelok Corporate, and I will be your moderator for today's webinar, which is entitled Fluid System Solutions for Hydrogen Applications. Hydrogen can be challenging to contain and manage in applications throughout the value chain. That includes production, compression, storage, distribution, refueling infrastructure, and on-vehicle applications. These challenges include ensuring operator and end user safety, leak-tight containment of small molecules under pressure, a wide range of storage pressures, and rapid thermal changes that arise from these pressure changes. Understanding and overcoming these challenges is critical for hydrogen producers, equipment and vehicle OEMs, refueling station owners, and the manufacturers and contractors who support the growth of the industry around the world. Today's presentation will discuss the critical considerations for fluid system components with a focus on fitting technology used in hydrogen applications and systems. These include the unique nature of hydrogen and the challenges it presents for fluid system integrity, how fitting design impacts the overall safety and effectiveness and the system, roles of the material science in ensuring long service life by resisting corrosion and hydrogen embrittlement, and the critical performance characteristics of fitting components and what to look for when selecting the right fitting technology for overall hydrogen system integrity. Just some general housekeeping before we get started. Following the presentation, we will have a short question and answer session. So if you have questions, please just type your questions into the meeting chat box and remember to click submit, and we'll get to as many as we have time for at the end. So with that, I will turn it over to today's presenter, Chuck Hayes. Take it away, Chuck.
Good morning, everyone. My name is Chuck Hayes. I've been working with Swagelok for about 32 years, primarily in the last 15 years to 20 years in the clean energy and hydrogen and natural gas industries. I am the global technical lead, and I'm a member of many different standards committees in North America, both CSA, the CSA committees for both hydrogen and natural gas, as well as TC 197 in Europe for the standard committees. So I work in a lot of different places in a lot of different areas and help customers around the world with their solutions. So let's get started and have a conversation. Today's truly just a conversation talking about hydrogen and how to choose components. So we're going to start off with the unique nature of hydrogen, and hydrogen is really one of the smallest molecules in nature. It is not the smallest. The smallest molecule is actually helium, because helium comes as a single atom. Hydrogen in nature comes as H2 when we see it. So remember that we've got to deal with a few different things always when we deal with hydrogen. We want to talk about safety, and escaping gases can pose some safety risks. And we do have end users interacting with hydrogen and hydrogen dispensers during refueling processes when we're dealing with vehicles. That's a little bit different than we see in other industries. Typically in other industries, when we deal with high pressure gases, we've got people wearing yellow vests and hard hats and steel toe shoes, and they're very highly trained. And in the hydrogen industry, if we start doing light duty vehicles, as we do in many places around the world, you could have your grandmother pull in and start fueling a vehicle at minus 40 degrees C and filling it up to 875 bar, which is over 12,000 PSI. Those are things that aren't usually seen within the gaseous industry in our world today. So we want to be efficient. We want to be able to utilize our hydrogen well and not waste it. So we don't want to be leaking it. We want to watch out for things like hydrogen embrittlement and how that works. We'll talk about that a little bit more later. I do have a graphic on this slide. I kind of like it. It's showing an H1, so just a single hydrogen atom, and its relationship to the size of a golf ball is approximately equivalent to the size of a golf ball to the size of the planet Earth. So if you think about it, it's very, very small. These are very, very small molecules and very, very small atoms, and we have to do some special things to be able to handle them. So, whoops. One thing about hydrogen safety, and we'll talk about this just briefly. I'm not going to go into much hydrogen safety. If you need to look into things for hydrogen safety or understanding setbacks and so forth within construction, great place to go is h2tools.org. It's a center for hydrogen safety. They've got lots and lots of information out there, and that saves me from having to talk about it here. So let's move on. So we're going to talk about leak tight integrity. So when we talk about sealing areas, we do have, hydrogen and fluid systems can leak for a variety of different reasons. Leaks happen. They happen in sealing areas. We have a thing called permeation, but good design can really help mitigate those effects of those leaks. But all solutions are not really created equal. And we're going to build up some basics and start at the very beginning and talk about leaks and talk about where they come from. So the first thing to talk about is really this concept that we talk about, which is continuous pore structures. What does a continuous pore structure mean? Well, if you look at the bottom, sorry, it's in 2D. It's kind of hard to graphically to show, but if you have two surfaces come together, there's peaks and valleys on those surfaces, no matter how smooth they are. And what happens is those peaks and valleys can touch and leave you with little caverns in between, little pore structures in between. And if they're connected, the gases will work their way through and leak out. So the more you smash them together, the more you bring them together, the less and less you have, and the less continuous they become in those pores, and the less leaks you have. So one way to be able to deal with that is to go ahead and employ things like plastic deformation of metal surfaces. And that would be things like burnishing. You bring the two surfaces together that knock down the high points and fill in the low points. And that's the way we create seals and things like Swagelok fittings. It's important to be able to do that. You need to have surfaces that can slide along each other in order to make that happen. And we'll see how that works in different styles of fittings, or doesn't work or can't work. And we'll talk about that in a second. In valves and other components, we typically employ other types of items like plastic or elastic, viscoelastic, different products, things that deform. So rubber will deform when you put force onto it, and that'll fill in some of those voids. A bad way to do it is actually with grease, and we'll talk about that as it's used both in valves and fittings in a little bit. So let's talk about permeation. Permeation, or other folks have called it diffusion, which is actually a better term. I like that better, but permeation is typically used within the industry as a term. Within metals, we'll start on the left-hand side and talk about lattice structure in metals. Metals have a crystalline structure. Those crystals are very close together. However, there can be, for very, very small molecules, ways for them to move in between the different grains within that material, the interstitial bounds. Hydrogen has a tendency to, under pressure, when it gets up along the surface of a metal, it will disassociate, so it'll break into two hydrogen ions. Those ions move into the metal, and they pretty much hang out there. And there they can start doing damage in a variety of different ways. They all fit under the general term that we call hydrogen embrittlement. Hydrogen embrittlement was a term coined back in about 1852, and that term was coined because what they saw when they were dealing with metals and hydrogen is when the metals failed, they cracked, and there was cracks that were formed. They happened to happen faster when hydrogen was introduced, so therefore it was assumed that hydrogen caused cracks and cracks caused failures. It's not necessarily the way it works 100%. The way the research has changed, there's a few different things that can happen. Hydrogen can actually work on the corners of where the cracks are, and it can help break down the bonds of already weak molecules where they're bonding together. And it can also go, so that's a hydrogen-assisted crack propagation, but ahead of that, it's also helping break down bonds and what's called hydrogen localized plasticization, where it's breaking down in local areas. It can also go in metals that are not pure. So if you come into, say, a cast material that might have a ferritic percentage of molecules inside, the ferritic and the stainless boundaries, ferrite and the austenitic steel boundaries, it can actually come in and start breaking those down. So hydrogen can work on breaking down materials. It will happen. It happens at all pressures and all concentrations of hydrogen, but really having the proper forms of the metals that you're using, and we prefer a 316L blend that we'll talk about in a minute or two that really helps resist that function taking place. Things happen again when you're dealing with rubber. So rubber, we're going to talk about in the middle. You notice the structure there is not as clean. If you think about rubber as a whole series of different long molecules coming together. They're bonded and they're cross-bonded between them or cross-linked, but the hydrogen will come in as dihydrogen, come in, it'll hang out. Depending on the structure of that particular rubber, it can do a few different things. It can help break down bonds if they're very weak, but it can also come rushing out under pressure. And what it does is it does a little bit different than what we hear about in other industries, which is explosive decompression. The results are very similar, but what it actually does is it blisters the material. It actually blows it up like a kid blowing a bubble of bubble gum. So what you'll see is that, and then it can actually rupture, and it'll look very similar to explosive decompression at the end. But the hydrogen can get there. The other worst thing that happens from a designer perspective is certain rubbers can swell at exorbitant rates. because they suck in so much hydrogen. So you can get rubbers that swell up to 70%, and that doesn't work well if it's in a race or in a small confined area to be able to be creating a seal. Some rubbers actually shrink as well. So having done proper hydrogen testing of different polymer materials is really critical. What we found is that first of all, hydrogen testing is very expensive. We've done a lot of different testing right now. We see that certain materials work really, really well. But to just put an example, just saying a trade name for a material like a FKM or a Viton isn't enough. We've done testing on 5 or 6 different types of Viton, and out of that, 3 would have passed and 2 failed. Exact same requirements for it. Just depends on the actual compounder's formula. So it comes down to manufacturer and compound number is really what it comes down to. Sorry, supply chain people, but that's really the way it works. So just be very aware of that. Just saying one material should work well doesn't really happen. And then finally, when you're looking at permeation and leakage, leakage will actually come between materials, as we started to mention before, and the hydrogen will come out as dihydrogen and leak, as we see in the right-hand picture there. But as we talk about leakage, we want to talk something else about that, and that's about leak paths. This is a model that's shown actually in Swagelok tube fitting manual. I actually clipped this particular version out of a Hydrogen Europe document. I kind of liked it. They used us as a reference at Swagelok, but there's a lot of things here. You can do some calculations. We're not going to talk about all the different letters. I want to talk about one in particular, which is the L dimension. If you see on the pictures, the L dimension on the left-hand side is on a coned and chamfered type of fitting. That L dimension is fairly short. And it runs down between 2 solid pieces. In the difference in the right-hand picture, where you have the L being very long on both the tubing and on the body of a Swagelok 2-ferrule fitting, that L dimension being long helps with the continuous pore structure. So having a long seal area with a high level of stress on it maintained is the way to be able to maintain a good seal. So we've had a couple things. We've had continuous pore structure, we talked about permeation and leakage, and then we've talked about leak paths. So those all come together to create a good seal that will hold against hydrogen and that very, very small molecule as we go ahead and do design. I start here when we talk about different fitting designs. Cone and thread fittings are in the industry. They've been used in oil and gas industries for years and years and years. It was actually created as a project with the U.S. Department of Energy back in 1918. They were doing a nitrogen project for both making nitrogen for both munitions and for fertilizer back at the time. And at the time, if you think about machine tools, they weren't very good. Threaded connections didn't work really good. They leaked like crazy for small molecule gases. They are smaller molecule, being nitrogen. They came up with this and it worked pretty well. One thing that people say that they're misinterpreting is that everyone says this is the industry standard. Well, guess what? There is no industry standard. It's kind of been adopted as a standard. It's de facto a 60-degree taper, but there's no actual numbers on it out in the industry. There's only one standard we've ever found, and that was a deep down well or deep down ocean floor application, and it only shows one size, which is 9/16. So let's walk it through real quick. Here's what happens. We're going to stay on the left-hand side of this picture. There's 2 different pressure ranges. That side goes up to about 20,000 psi. The other side goes up to 60,000 psi. So you basically take a piece of very heavy wall, 1/8 hardened tubing, and you cut a cone onto the end of it. That cone is done with a series of different types of tools, and that cone is important by its surface finish to reduce continuous pore structure and the angle that it has in order to make a good seal. Behind that, there's a thread. It's a left-handed thread, so that's the one that always makes your head go crazy when you turn it on backwards every time. But you turn it on backwards, and that holds a collar. And the collar is there for one purpose, which is that the gland pushes on the collar, which pushes the tube forward and it pushes it into the body. And therefore we get our force and load onto the sealing surface. So basic, simple idea. Now, there are people in industry that say, this is a great fitting because it can't blow off. That's not true. That would assume that the threads can't tear off. Assumes the thread quality is of high quality. Assumes the collar is of high quality, which aren't always true. So if tubing is undersized, the threads will not have the same strength. They can tear off. There's a few different things that can also happen. If the collar has to be manually placed in position, that comes down to operator how the operator does it and the operator's skill. So where that collar ends up, if it's too far close to the cone, it can actually hit the body and the cone will not seal properly. If it's too far back, the gland may not thread and engage enough, and therefore you don't get enough threads of engagement on the gland. So there are a variety of different ways in which just the assembly of this can cause a problem. The other piece is that the back of the gland and the front of the collar have to rub against each other, or they do rub against each other. And the point of that is you need to lube that. If you don't, especially on small sizes, and I did not believe this until about January of this year when I saw it actually happening, what can happen is they can bind up the tubing onto the collar, and then it ends up starting to twist the tube, which is pretty weird looking. And you can see actually the lettering on the tubing starting to twist. It can happen on larger sizes as well. That's not a good thing. So you have to put lube there. This brings up a problem. Folks will also say, well, I've got lube there. I should probably lube up the primary sealing surface as well, because I don't want those two surfaces to gall. Galling is a process where two metals come together and then they share electrons on the surface. In other words, they weld themselves together, and that is not good either. But as I said earlier in hydrogen, what happens with using a grease is hydrogen likes to push out any of the greases that are used on those surfaces. So hydrogen will push out the grease over time, and that if it was filling in your continuous pore structure, it will start to leak over time. Okay, that's why, one of the reasons why, very often when you build a hydrogen system, you'll go ahead and you'll do it. You'll do your factory acceptance testing. You can get it to pass. You'll ship it. Typically 10% to 20% leak after shipping. You tighten those back up. 3 months later, all of a sudden you've got fittings leaking all over the place because they were greased up and the grease is now gone. So that's one of the different ways that cone and thread has a problem within this. The other thing is that remember we talked about the length of the seal. Well, the problem is that the body has a particular angle on it and the cone has a different angle on it. Very often the body will have a larger angle, so that might be a 62 or 63 degree cone, and the cone on the end of the tubing might be 57 degrees. They're both rigid, so they can't slide against each other. So what literally happens is you end up getting a single point of contact at the bottom of the cone that will gouge into the body. That process is something we call coining. The way to describe coining the best is go back to Roman times, take a piece of metal and a coin and a die with a picture of Julius Caesar on it, smack it with a hammer, and you got a picture of Julius Caesar's face sitting there on your coin. If it's not deep enough and you want to make it a little bit deeper, you hit it a second time, and if you get it perfectly lined up, it'll be deeper. If not, Julius Caesar has two noses. That's not good. Same way when you have a coined surface on a fitting, if you try to remake it, it's got to go right back into the exact same spot, or else it's not going to seal, or you have to go deeper. So at some point you're moving metal, but you're moving metal that's going to damage one of the two surfaces. If it's the body, that's a bad thing, especially if it's a body of a very expensive valve, that if you try to remake it, it won't seal. So there's issues there. Finally, there's a thing in here called a weep hole. I like to call it a leak port because primarily when you look at these fittings in gas, well, they leak. You don't want gas pressure building up in that chamber in front of the gland because that could cause the whole thing to blow off. So therefore, there is a leak port. We do see significant leakage often in the cone and thread fittings out in the marketplace, and we do see another phenomena taking place. So what's very interesting is we found some technology reports being done about cone and thread, about leakage. So what we keep hearing in the industry, I was on a trip in Asia about a month or two ago and probably met with 15 different customers, all of which said they saw this exact phenomena taking place. Everything's sealed, everything's fine, system heats up, system starts running, and then all of a sudden you're setting off hydrogen alarms. You turn it all down, you go in, you start leak checking it, and everything's sealed. Well, how is that possible? How can something be leaking at one point and not leaking later? We think we may understand part of what's going on here, and this comes from this study. This is a slightly different fitting technology, but the physics are all the same. So up in the upper left-hand corner, what you see is a preloaded tension. So high tension, what this is von Mises stresses. Basically think of this like your radar for a storm. Red is really heavy rainfall, real heavy load. So everything that's red has a really heavy load on it, and that's good. That makes a good seal. If you go to B, which is over on the right on top, all of a sudden everything starts turning yellow. And if you look at the bottom of the body where the seal is, it's almost all green with only a couple members being yellow. The reason is this thing has been offset by 0.3 millimeters, not very much in the up direction. So if you see them, they're not quite lined up. Put a side load on it, it can start leaking. That's not the crazy part. Okay, you side load it. We've always known Conan thread is not good in vibration. That's a pretty well known in the industry. But the weird thing is in C on the bottom, when you come back and you relieve that load, all of a sudden the seal comes back. This is indicating that you can have a seal made and broken many, many times in the Conan thread. It's wobbling within that area, and you can see leaks come and leaks go. We've seen this in a lot of different customers in a lot of different places, and it's just something to be aware of that Conan thread does this. There is a possibility to put something called an anti-vibration collar on the back. It's going to triple the length of the fitting, and they're kind of expensive, but that'll keep that side load from taking place. It makes it really tricky to design it into your system because it's going to add a bunch of space. So a lot of these reasons come together for why Conan thread may not be the best thing when we're dealing with small molecule gas. Works good for oil. It's a big, thick molecule. Not as many problems with it. Swagelok sells Conan thread. We'd be happy to sell them to you, but probably not the best thing as we're dealing with these small molecule gases. So there's a couple different things here. So there's no international standard for Conan threads. So the fact that everyone thinks you can interchange different manufacturers together isn't really that great of an idea. They're not all made the same. They're not all holding the same dimensions. So that's one piece. Coning is performed by hand and in the field, sometimes with benchtop tools. They're not done on large rigid machines in a factory generally, unless they're small nipple pieces that go between other ones. So like the coned portions of them are not generally as high quality and not as high quality surface finish and so forth. And on the side here, there's a kit that shows how to do this, a coning and threading kit. We're happy to sell you one of these too as well. Lots of different pieces, parts to them, lots of skill that comes in place with them. You've got to make sure these tools stay sharp. You're squirting a bunch of oil on this part, oftentimes ones that have hydrocarbons in them, which then you have to get back off of your parts before you put them into a hydrogen system. So lots of different variables that come into play to make up for making just one single joint. So just letting you know, there are issues when you're dealing with Conan thread. So let's talk about some other fitting technologies that are out there. Just real quick, we're going to run through them. Tapered fittings, NPT fittings. A lot of people say don't use threaded connections. Well, in some cases, yes. In some cases, no. The tapered fitting actually wedges in two different directions. So it wedges both down as it goes down into the wedge, and then on each thread wedges itself. We have some papers out there that we've seen which have said that, generally with two full wraps of a high quality Teflon tape, like Swagelok Striptease, it actually said in the paper, I love when they mention us, that these will work very well. I've done hydrogen testing on vehicle on 1/4 and 3/8. They work really well. 1/2 inch sometimes get a little bit more difficult. The larger you get, the amount of load that you can put into the seal, into the wedge gets more and more difficult. So on the smaller sizes, they work pretty good. So they can work and they can hold up fairly well. Some other type of things, parallel threads. This is one example of an ISO parallel thread, a British standard parallel pipe. This one happens to have a seal with an O-ring on the top. I show that because of just understanding how that gasket works. Remember what I said about rubbers earlier and who makes them and what the formula is? These are general commodity items. They're about €1 a piece, $1 a piece out on market. We have no idea what the rubbers have specifications, but they're not high quality rubbers necessarily. We're relying on that to make the seal. I could probably go ahead and develop one, but it would be so expensive nobody would want to buy it that would actually work here. So the other problem is if I look at this from a fitting development standpoint, I've got somebody making that body. I've got somebody making the stud, somebody making the gasket piece, the little washer behind it, and the nut. So there's 5 different people involved in this process, and if it leaks, whose fault is it? And then we've got an assembler, so there's 6. So there can be a few things. That being said, lots of folks use this, especially in the 350 bar threshold world and lower, because this is very, very often what you find on your transmitters, your pressure transmitters. So it can work. There's other ways, other variants of this that would just be an all metal seal. There is also one that has gaskets on the bottom of the face. So there'd be a metal seal or an elastomer seal down on the bottom. So it would be a flat bottom that this would seal against. So there's a few different ways that you can see this out there. And yes, parallel is spelled that way because that's where I got it from a European spelling. So that's been mentioned before. Okay. Later in here, you see the tapered with the other parallel spelling. And this one is a parallel female thread with a tapered male, the answer there is just don't do it. That's a silly idea, especially for hydrogen. So not very many people do it anyway, but I don't recommend it. A couple of different things about flare fittings. Okay, we talked about the hard edge, the hard fitting going into a hard cone in the cone and thread. Same thing here. Flared fittings in lots of different aspects. You'll see in the left hand a flared fitting going into a flared body. You've got to hope there's no sliding surface on here to burnish. They show on the bottom that it would be sealing along this red line. Well, I don't think it's going to be sealing on that entire area unless those surfaces are absolutely perfect. So you have other issues again. There's other ways to make flares. You can actually flare out the tubing in a variety of different ways. All of them have the same issue, hard surface on hard surface. Nothing is conforming or moving or sliding to get you a good seal. And these are just inverted versions of the same exact fitting, the two. When we go over to the end, this is a ball on chamfer. Some people really like this. There's some automotive companies that really loved this kind of idea because they could have all kinds of misalignment where their fittings came together. The problem is a ball into a cone. If you go back to grade school, if you did a ball into a big cone in 3D, you would see that all you had was a single line of contact. So again, single line of contact in cone and thread, not good. Single line of contact in ball and chamfer, not good. Single line of contact in flare on flare is not good. All of those have very, very short lines of contact. You've got to hope that you can make that seal and continue it. You do not have that long L to be able to knock out that continuous pore structure. A few other types of fittings. There's this O-ring face seal fitting, originally patented by Swagelok in 1963, I believe it was, as we call it a VCO fitting. It's out there in the market. It's been used a whole bunch. There's an SAE number for it, which I don't remember off the top of my head. Used a whole lot in natural gas, in the natural gas industry for gaseous fuels. Worked okay. Interestingly, that when we talked to the German auto manufacturers, they said absolutely not allowed on hydrogen. So if you want to take their experience on it, that'll tell you right off the bat. Here's the thing: you're relying on an O-ring to give you the seal that will permeate constantly. So that's one piece. Second one is the way that thing actually works is it takes pressure to take that O-ring and push it into the seal to make it seal every time. Well, in hydrogen systems, we generally have pressure cycles, and those pressure cycles mean that every time it pressure cycles, it has to reseal. So if you have 100,000 pressure cycles in its life, it's got to reseal itself 100,000 times. That's a lot to ask for that poor little O-ring. So not something great to work with. We really avoid O-ring face seals if we can across the board. And finally, there's this SAE J1926. It's also ISO 11926 fitting. This is a parallel thread with an O-ring up in the groove on the corner in a boss. It actually creates what's called a fresco conical seal. The one thing to be aware of is that the body actually is cut with a special reamer. It's got a double tapered angle on it. It's not just a 45-degree angle. So it's really critical to make sure the body is right, or else this doesn't work. What happens is you load it down and you actually load up the shoulder. So the body of the fitting will touch the shoulder of the body that's going into, and that's where the load comes that is used by pulling on the threads. Okay, the one problem there, if you are putting one of these in to aluminum, and that aluminum, and you're trying to hold a 700 bar system. So on a 700 bar vehicle application, that actually means it's 875 bar maximum allowable working pressure. At 875 bar, you are very close to the pressure load interacting with the face of the fitting, being very close to the load that you're putting on the shoulder to hold the fitting in place. If there's any differences in lubrication on the threads, preloading, torque, so on and so forth, or if you've over torqued it and stretched the threads and then they relax a little bit, what can happen is these fittings can back their way out. They can actually spin their way out. And it actually is pretty interesting that after about 1,000 pressure cycles, between 1,000 and 1,200 pressure cycles, a gap will be large enough on it that the O-ring will come squirting out. So a lot of people think that's an O-ring problem. It's not. It's a system design problem. We've only seen one or two real major issues with this in the field. In an application where one did back out and caused a leak on a vehicle when it was in fueling, set off some alarms and scared some people. But just be aware that these at the higher pressure boundary, while they can work, you have to be very, very careful. People will often want to lube up that O-ring and at the same time lube the threads. That changes the entire friction formula on the threads and what your torque is actually applying and what's happening. So if it's going into aluminum, be very, very careful at those higher. At 350 bar, they work fine. Just be aware that you want to make sure that that elastomer in there has been tested with hydrogen. Okay, a few other things. Cutting and biting style ferrule fitting technologies. Basically what this does is you take a piece of metal with a sharp nose on it, and it bends like a banana and bites into the tubing. You end up with, on a single biting ferrule, you'll get a bite, you'll get a deep groove put into the tubing, and you'll get a single point of contact along the inside of a body. That's done as the nut is pushed in. So a couple problems here is where that bite takes place, ends up being a stress riser. And what can happen over time, and I'll show you the testing that we do to prove this in a little bit, that'll cause a crack to propagate if you've got any kind of torsional load coming down that tube, and it can snap. Same thing with a twin biting ferrule. It just, you got two bites, two places, but you get a little more contact on the body for holding back your hydrogen for leakage on the front ferrule. The last one on the bottom is a friction type fitting. This is what you find in your home stores. They don't work under my sink. They don't work on hydrogen. Not a good idea, but a friction style fitting is not really the way to go. So that just relies 100% on friction. All right, we'll move on. Other technologies that are out there, there's a thing called a diesel style fitting. Basic premises are the same all back through the other ones, and we'll use this to talk about some things like torsional. It's a 60-degree taper again on the body, but what they do here is they take and they manipulate the end of the tubing to make it look something like a ferrule or a ball nose or some other form that would go into the body, like basically all the forms we just looked at in the previous slides. These have been used in diesel for years, but we're seeing there's some potential issues coming up with these when we deal with hydrogen. First one is it's a rigid fitting onto a rigid body, all the things we mentioned there. The other piece is they worked really, really well because if you look up in the upper right-hand corner, this is what a diesel fuel rail piece looks like. You got a bunch of really small pieces. They bolt together. They bolt onto the top of the engine. When the engine moves up, they move up. When the engine moves down, they move down, left, right, up and down. There's no real extra loading putting into where that joint end is. But if you look at the bottom, that would be a light-duty fuel rail or light-duty front-to-rear hydrogen line with 4.5 meters long on a vehicle. And if you think about the way vehicles work, the vehicles can move, they bend, they move. There's movement in them. If they didn't, they would crack. So the fuel lines are moving as well. So what you can actually do is put load onto the end of the fitting. There's a way to be able to test for this. This is not your standard vibration tests. Your standard vibration tests are X, Y, and Z. Those are called planar torsional flexure fatigue tests. They can show you whether a panel that's welded together is going to break. To check fittings, you actually have to do something a little bit different. And this is called a rotational flexure fatigue test. It's labeled by an SAE test. So there's an SAE test, an ASME test that does this, as well as SAE aerospace test. So I know there's some folks from the aerospace industry here today. This test is required for all of your fittings that are done in your wing structures due to the way the wings move, obviously, dynamically within flight. Here's the thing. I can have a fitting. If you think about the way this works in physics, I hold a fitting stationary in place, and the other part of the line, down the line, can move. Well, it can't move left and right across the screen because it's holding in with the fitting. If it didn't, then you'd have another problem. It can move in and out of the screen and up and down. Those are the only degrees of freedom that are left. So with that, I can simulate that by doing a rotation. That rotation in this test is set up by actually taking and putting a strain gauge on the tubing. What that does is takes out the effect of different types or different batches of tubing, and we actually set a strain, and then we set whatever that offset is for the rotation, and then we rotate it. So what happens? What that does is it puts a load down on that fitting, and it'll put a load down near the face. So if you just have a hard fitting sitting in a cone, it might vibrate, it might move, like the cone and threads. Those have issues with this test. Ones that extend beyond the ferrules, like a Swagelok 2 ferrule fitting, are better supported, and then the fittings have a collating action that protect the bite area. I mention that because the bite area on the bite fittings will generally crack there fairly soon. This is a 10 million cycle test that takes place. The tubing is pressurized during the test, and it can actually run impulse as well. So this actually is a test that shows what is actually happening in the life of the fitting that is being tested, and it is actually probably the most appropriate way to test a fitting to prove whether it's going to be able to handle fatigue testing out in the marketplace. Okay. Before we go on any further, as we're talking about fatigue and we're talking about material characteristics, let's talk real quick about material integrity. We have worked with a variety of metallurgists, both internally and externally. We've worked at Sandia National Labs for years, providing materials. And in fact, our PhD metallurgists have taken and published many papers with Christian Markey, who's the expert at Sandia in material sciences for hydrogen. We developed early on in the early 2000s a material that is optimized for hydrogen. This is our standard material. It's actually patented. It's a 316L stainless steel alloy. So it meets all the requirements of both 316 and 316L. We do that by doing a few different things. The first one is the nickel content. So when you're dealing with nickel content in stainless and hydrogen, nickel stabilizes the crystalline structure inside the steel. The requirements for ASTM for that are between 10 and 14% nickel. We set our minimum at 12. There's a lot of different discussion in the industry about where do you set your nickel requirements. There is a curve, and if you get to that curve, it starts getting very flat. Above 12, below 12, you start getting into a lot of effects of hydrogen affecting the material. It drops off like a cliff. So above 12, you're safe. Anything above 12 to 14, there aren't much gain between 12 and 14. So we stick with the 12 range. Nickel is important because nickel is the single most expensive element inside the stainless steel, and nickel has had some problems ever since a little war started in Eastern Europe, where a lot of nickel was coming from into commercial applications. So the spot buy commodity on nickel has been very expensive over the last couple of years. So some people have really tried to cheat back on it. Also, when you buy just general 316 from a general steel seller and you don't specify what you want your nickel rates to be, you are going to get something as close to 10 as you can get, like 10.01% nickel, to be able to make their process more profitable. Okay, one of the other pieces in there is chrome. So chrome is a minimum of 16. We bump ours up to 17. Chrome is also very expensive. What that does is helps with corrosion resistance. That combined with moly help on corrosion and really fight against those problems with corrosion. Corrosion also can start the beginning of what eventually will be a crack propagation or a problem with hydrogen attacking the materials as it starts breaking it down. So corrosion is very important. And these two elemental discussions we have are there to be able to make what we feel is the best material on the market. You will hear sometimes people talking 13% nickel, and they talk about one other number, which is a nickel equivalency. That nickel equivalency, the magic number is 28.5. Well, nickel's worth 1 on the scale, so if you go from 12 to 13, you go from 27.5 to 28.5, and we're always at 27.5. So we're right at the same place. If you look at the different metallurgy graphs, basically the dots pretty much overlap each other. So we don't feel that extra small amount is of value, as much value as balancing the other elements within the steel. The 316L also balances the sulfur and the carbon levels. That allows for a high ability for weldability. So just putting out there, this is where we feel it is, and we believe that's the most appropriate place within the market. So let's talk about tube fittings. We've talked about a lot of other fittings, and I want to talk about why we feel the Swagelok tube fitting is one of the best designs. So to start with, Swagelok tube fitting has 4 basic elements: a nut, a back ferrule, a front ferrule, and a body. Add the 2 other elements, which is the tubing and the operator who pulls it up, and you've got the 6 things that make up a tube fitting. So there's 3 main advantages. We call them the tube fitting advantage that we have within the Swagelok fitting. It's tube grip, gas seal, and vibration protection. If you look at the front nose of the front ferrule, what you'll see is 2 lines here. That's where we get our gas seal. Very long sealing areas. And a couple of things happen here. So in the bottom little picture, what you'll see is the back ferrule coming up underneath the front ferrule. When we make up this fitting, the nut will push against the back ferrule comes up under the front ferrule, pushes it forward. They all move about 58 thousandths down as it's made up. And what happens during that process is a few dynamic things. The nuts and the ferrules move both plastically and elastically during that process. The back ferrule comes under the front ferrule, and you notice it ride up that little ramp there, and the front ferrule lifts. So the front ferrule has a different angle than the body. So when it lifts up, it slides down and it burnishes down that body all that way, creating reducing the continuous pore structures and creating a very tight seal. It does the same thing along the tubing on the bottom, and that front ferrule gives us that gas seal. So I've been in development of product here at Swagelok for over 25 years, and gas seal performance, just to let you know, is the most difficult thing we do. And gas seal performance for the smallest molecule gases is even more difficult. And this fitting has been used very effectively within the hydrogen industry for the last 75 years. And we've been involved in small molecule gas and hydrogen for that entire period of time. A little bit different industry we have today than it was back then, but we've been involved for that entire period of time. What you'll see beyond that is the back ferrule. The back ferrule comes in and it actually does a process called hinging and colleting. It'll bend in the middle, and at one point, when the front ferrule stops moving, the back ferrule will actually turn and dive into the tubing. So we do get a dive into the tubing, but it's a little bit different than the bite you see in a bite style, because it also collets right behind that bite or that dive. And what that colleting does is holds onto the tubing very tight, like you do with a drill inside of a machine tool. It's like a collet. So it'll hold it very tight, and it goes ahead and protects that area that could be a potential stress riser, giving us great vibration protection. So we've got, and the tube grip comes from that bite and the collet as well, giving us, when we talk about tube grip, that gives us our pressure performance. And as you see here, a few different things happen. When this fitting is pulled up, ahead of the front ferrule, there's a slight swell on the tubing. That means the tubing can't push back through the front ferrule. The back ferrule goes ahead and makes these few different dents in the tubing, meaning once the ferrules are swaged on, they're permanently on there. So that's how the mechanical grip portion of that fitting works. In the end, one of the things that happens, you wonder, how do you go ahead and cut a material with the exact same material? Well, you have to have a harder surface to be able to do that, or else they just smash together and they gall. So we use a patented process called SAT12, which is a low temperature case carburization process. We actually go ahead in vacuum ovens, create a vacuum, remove the clear oxide that's on the outside of the ferrules, and force carbon into the surface. But in the end, what we do, it's very small, very thin layer. So the white layer you see in the picture here is actually that case carburization. The little dots at the bottom is the hardness testing we do with it. So those are micro hardness testing dots after it's formed. What this does is gives us enhanced corrosion resistance, tool-like steel hardness. So this is like a Vickers of 1600, which is about what tool steel is, allowing it to go ahead and cut into any hardness of tubing, or the general hardness of tubing that are allowed within the standard, and get us our tube. Our dive that we need. It also remains ductile under all time, so it doesn't crack. There are some other ways to be able to harden surfaces that are chemical, but they crack under when they go ahead and start moving dynamically. That's bad. Again, we said cracks in hydrogen are bad. One last thing about the SAT12 process, which is kind of cool, it does use hydrogen within the process. So we developed this over 25 years ago. We do generate our own hydrogen on site, so we are also a hydrogen producer and use hydrogen every day in the processing of our ferrules. So that'll get you up to, so the standard tube fitting will get you, depending on what the tubing is, pressures up to 9,000 PSI, but generally we consider it to be part of the 350 bar or the H35 pressure class. When you start going above that, you start getting into the 700 bar pressure class, you need to move to a different fitting. This is the Swagelok FK fitting technology. This was designed for hydrogen. It was designed back in about 2000, started in about 2004, 2005. It was actually designed in cooperation with a group, a consortium of automotive companies that were looking at developing the EIHP standard, which was the predecessor for EC79 and predecessor for the hydrogen standards. So basically, you'll notice this looks a little bit different. You still have two ferrules on it that you can see in the lower left, a rear ferrule and a front ferrule, and a nut. But it is it's a female body, so a male nut, and it's got some strength characteristics to be able to handle the higher pressure systems. You'll notice also that the front ferrules are red. We actually do that through changing a thermal oxide on the surface so that it's discernible between there's a difference between the look of this ferrule versus the other ferrules on standard fittings. So if you have them both in your shop, you can actually tell the difference between them. So when this fitting is made up, we'll go ahead and look at what happens here. Little video of what happens when this is pulled up. So when the body is pulled up, what you'll see is the ferrules moving. I'll play this a couple of times here. The front ferrule, if you look on that side, it goes ahead and slides along that body and creates a very long seal along the body. It's a different angle when it first starts. So you notice that it lifts up and does that. You notice something else in the front ferrule here that's a little bit different. It does go ahead and dive into the tubing as well. So we actually create our own surface on the tubing. The tubing for this product happens to be 1/8 hard tubing generally. So this is a harder tubing. So because of that harder tubing, we have to SAT 12 that front ferrule as well. Rear ferrule, you'll see it doing its action and its craziness. So it goes and starts and changes its geometry as it slides in and bites. It's a deep dive into the tubing to be able to hold back the pressure. The other thing about the rear ferrules is they do stay partially elastic through their entire life so that it can pick up changes in pressure and temperature as it goes along. So it can deal with that variability. It also collets, and that gives us our ability to hold that pressure and protect that dive up ahead of it. So we get our tube grip in 2 different places, both on the front ferrule and the rear ferrule. Gas seal performance on the front ferrule, which is a very high level of gas seal performance designed for hydrogen. Vibration resistance on the rear ferrule. And so this fitting design was specifically, again, designed for hydrogen. It has been tested for on-vehicle performance up to 875. It's pressure rated up to 20,000 PSI and designed specifically to deal with this. Burst pressures at, depending on the tubing, it's anywhere between 3.5 and 4 times the pressure rating of the tubing. So that's a very high rate for your final pressure ratings. So when you're looking for something better than cone and thread, this is definitively better than cone and thread, and it's designed for exactly that purpose, especially in on-vehicle applications and high vibration applications where cone and thread is not appropriate at all. The FK series is great. One last thing about FK series, just because it's kind of fun, the original name was because we originally expected the pressure boundaries in the industry to be 15,000 PSI, so FK 15 KSI. Well, the industry's now switched and everything is in bar, so that kind of went away, and we rated the product to 20,000 PSI, so FK doesn't mean anything except the name of the series. So there you go. There's just some fun for it. Very easy to install. It's a 1-turn makeup or torque, so it's a makeup by torque or makeup by turns. So there you go. Final conclusions. Not all products are created equal when you deal with hydrogen. It's really important to understand that. Understanding leak modes helps designers choose what are the best products. And no matter how amazing the hydrogen future looks, a strong foundation is really critical because you need the right products to keep the hydrogen in place. So a lot of times people talk about hydrogen, what they want to talk about is these big plans and big future that's coming. But what really is important is understanding that having that strong foundation is the most important for success for everyone. All right, so we're down to questions, John.
Okay, well, thank you, Chuck. We will now transition to our question and answer portion of the webcast. Here are just a couple that we probably will have time for. What challenges are presented by thermal changes throughout the H2 fueling system delivery process?
So that's a great question. When we deal with on-vehicle, especially in 700 bar, because hydrogen has reverse Joule-Thomson effect. What happens is that as you fuel, instead of getting cold like many gases do when you go through that pressure change, it actually gets hot. So if I'm going to go and I want to fill a vehicle in 3 to 5 minutes, let's say a car, that's going to be filled between 4 and 8 kilograms of hydrogen on board, filling fairly quickly, I need to start at minus 40 degrees C. So that's also just how it happens to be minus 40 F for those that don't know that. So at minus 40 degrees is where we start. And during the fueling cycle, as it ramps up to a final pressure of 875 bar, it's going to see a lot of thermal change, and that happens in 3 to 5 minutes. So something that's going to be seeing thermal change in that period of time, having a fitting like an FK fitting that is able to handle that dynamic change, and the standard Swagelok fitting does it well as well. It can handle those dynamic changes within its design because of that bit of elasticity that stays in it. It's not rigid all the time. It can handle that very well. So it's a very high rate of change that we see, high rate of pressure change happening simultaneously. Both pretty nasty when you deal with designs, and both of those fitting designs handle it very, very well.
Okay, thank you very much. I think we have time for one more. Let's go with this one. How does the spring-back action of a two-ferrule fitting allow for slight movement and vibration without compromising the gas seal?
I think that answer was the same question we just had. So the elasticity in the back ferrule. The elasticity in the back ferrule really allows that to handle that spring back and that change in pressure and temperature, keeping that slight elasticity in it. Doesn't totally go plastic, and that allows for that spring back to take place and keep that system tight at all times.
Okay, well, we will wrap up at this point. Just a couple of housekeeping issues before we conclude. You can request more information and be connected with your authorized Swagelok Sales Center Service Center by going to swagelok.com/locator. You will be responded to within 3 business days. An on-demand version of this webinar will be available on swagelok.com on our webinars page. And as always, you can stay up to date with Swagelok by following us on our social media channels, which include LinkedIn, YouTube, and Twitter. Thank you all for attending today's webcast. We hope that you found it helpful and informative, and we look forward to seeing you again at our next Swagelok Clean Energy webinar.